So let's kind of strip away, sort of the black veil or the sort of black box about deep learning. Let's go deeper into deep learning. How does it work? How does deep learning work?
Yeah, so I think the most important thing you need to understand is we use what we call something called CNN, which is basically convolutional neural network, which is a stack of a lot of layers, a lot of hidden layers. And basically the idea is you have images of cat and dogs, and the goal is to say I want to know if this image is a cat or a dog, basically.
Right.
So your input of your model is gonna be the images of the cat and the dog, okay? Your output is gonna be the categories, the labels that we talked about before.
Right.
So it's gonna be either that's a cat or either that's a dog, basically, okay? And so you train basically a model with the association of this input and this output,
right?
Like the combination of your features and labels. And when your deep learning is trained enough, you have good metrics basically on it that tell you that this model is perfectly trained. You can do what we call prediction. So what is a prediction is you basically give now that your model is good enough new images, so an images of a cat or a dog, and the system is gonna technically tell me directly if it's a cat or a dog. So that's basically what is deep learning in a nutshell.
Gotcha. Okay, so it's really not magic then. It's just sort of it's math at the end of the day, correct?
Yeah.
So
the problem is an optimization problem, basically. It's a non-linear optimization problem. So what you want to do is you want to try to find basically a solution for this problem. The problem is there is no way to find an exact solution. So we try to find what we call an approximation.
I see.
Why we do that? Because these deep learning models are gigantic. It's millions and millions of parameters. So for example, for UNet, which is a special architecture of CNN, you have roughly 16 million of parameters.
Only 16 million.
Yeah,
right?
and that's a small network. You can get even bigger than that. So it can be huge. So you go into a multidimensional space, basically.
I see.
To do that. And to train that, there is no way mathematically that you can find the exact solution. So you do an approximation.
I see.
And basically what you do is you're trying to use an algorithm that is called gradient descent.
Okay.
And so why you want to do that? Basically, you have what we call a cost function. There is the loss function. There is definitely your goal of your problem is to find the minimum. And so the difference, this loss function is defined as the difference between the prediction and your labels. If this difference is close to 0, that means the too much, that means your model is perfect, and then you're very happy.
I see. Yeah.
And so the idea is to whenever you have this gradient descent, is to find to start with a random point and try to find the bottom of it, basically. Yeah.
Right.
And that's what we call the global minima. And this global minima, to find it, you start for this random point and you will try to find what is the deepest slope, basically.
Right.
To go to find the fastest possible this global minima. Yeah, this descent. And so you can be stuck in some local minima, but the idea is to try to do everything that you can to touch the bottom of your curve.
Exactly, to escape that.
To find the minimum, and then to find basically the best solution for your deep learning. And so that's what is deep learning in a nutshell on the mathematical part.
I see. Okay, and so those same concepts, right? We're using them for a myriad of different things, whether it be in the medical industry or in the car industry. We can still apply those same things to data, to seismic data, correct? Because instead of taking an image of a human's brain, now we can take images of the subsurface, right?
Exactly. So we apply this in seismic, but we can apply this also with the self-car industry, when you're trying to find basically automatically in real time to find the cars or the traffic lights or etc.
Right.
Also, for example, for in the medical industry, that you want to try to identify automatically where is the brain tumor in the MRI.
Right.
But today, Julian is saying, in Bluware, we apply this basically in seismic. So how do we do that? The idea is come back to the same principle that we have with the cat and the dogs.
Right.
So a geophysicist is gonna come and try to tag basically, it's gonna try to tag basically where is the salt on the seismic.
Right.
And that's gonna be what we call a binary segmentation.
I see.
Because you're trying to find the boundaries between where's the salt and where's the non-salt. So to come back to our problem we talk about with the cats and dogs, basically. So in our case, for example, the salt is gonna be the value 1, and the non-salt is gonna be the value 0.
Exactly.
And you want to learn, compared to the cat and dogs, this time you want to learn that for each voxel, each pixel, to say that this pixel on my seismic is a salt, or this pixel on my seismic is a non-salt, basically.
Right.
And that's what you do a binary segmentation. And then the association, or like now the features, there's gonna be this time the images of the seismic compared to the images of cats and dogs. And the labels, there is like what I just said, that basically this is like a salt, this is a non-salt. You send that to the deep learning, you train on this, and that's how you create basically your deep learning model.
Right.
But the last thing that is different now from basically the cat and dog categories is now you train like these gigantic images of seismic.
Right.
And the problem is these images are way too big, so we need to like get some subset of these images, what we call like patches, that we set to the deep learning, and we train that will constitute basically your label set. And that's what we do to basically apply deep learning on seismic.
Right, because those seismic volumes, they can be as small as say a few miles, but really they can span thousands of miles, if not thousands of kilometers, right? And
exactly.
So we need to decimate that to feed it efficiently.
Yeah, and it's terabyte and terabyte of data when you think about it.
And that's on the light side too.
Yeah.
Definitely.
For sure, yeah.
And what's absolutely fantastic about this is that it really helps reveal those finer details, because now you can come through those massive data sets, right, at large, and tease out those small subtleties within the data, understand what is the true distribution of my salt. But it goes further beyond that, right? That it's in any geological sense. It can be applied to faults, it can be applied to channels, really characterizing the full extent at a very high level of detail of the subsurface, which is fantastic.